way about the function of temperature according to the experiments. This is the equation for calculating the CP, and this is for CP. This is not for you. I think you should know. This is not so important, but we should know. There are three methods. Maybe we can say three methods to calculate the CP or CV. The one is the CP is equal to like this. This is a real specific heat. But there is another, maybe, this is not so important. We just know there is a real specific heat is enough for us, okay? And here, there is another average specific heat. As we know, for this one, okay, sorry. Here, we know if we use a figure, C, and this is the temperature. It's maybe like this. Yeah? It's not hard. Maybe we can say it is a little hard for us to use true or say a real specific heat. So we, for example, from temperature 1 to 2. So if we want to calculate the area, we can use this, the real specific heat, okay? We can use this one. We also can use the average one, the average specific heat, okay? Which is like this. I think you can understand this well, yeah? For example, I can use this one. Yes?
Yeah.
I can use this. This is the average specific heat. We can also use it, okay? And if you are interested in this one, I think you can try to understand what it is. But for in our class, maybe it is not so important. Okay? I mean, you just know it. You just know it is enough. And there is another one, a constant specific heat. For we know average heat is still related to the temperature. Yeah? For example, if we change the T2 to 3, and then the average heat will be changed. Yes? But do you remember when we are quite young? We know. Do you remember this? Q is C. Do you learn this equation? Yeah, we learned this for a long time here. And this C is a specific heat, and it is a constant specific heat. Okay. Now, when we are graduate students now, we should learn there is an average specific heat and there is a real specific heat. But we still use the constant specific heat in our class. Okay? So we just remember one thing. The C is a constant value. Okay? I don't know whether you can understand me now. I just say when we talk about a lot here, we just need to know there is a real one, so the average value, and also a constant value, but we use the simplest one. Yes, this is the kind of thing that we use. So, in the next, we are trying to calculate the internal energy, the enthalpy, and the relationship between CP and CV. So, maybe, okay, here. This is the result. But how can we get this equation? Okay, we'll try to show you. I think you may remember we had learned 6 state parameters. Yes, 6. Do you remember that?
Yeah.
P, V, T, U, S, H. Yes,
Yeah.
we have learned 6 state parameters. But this 3, we call it the basic state parameter. Yeah?
Yeah.
So, in the future, because we also know, for the engineering thermodynamics or for our class, we want to learn how the energy or how the heat transfer to the work. Yes, this is our aim. How the heat transfer to work. Yeah. So we want to calculate all these parameters. Maybe we want to calculate the heat. Yeah, how the heat transfer to work. Yeah. So we wanted to find this. So how to calculate? Yes. And also S. We don't know. We want to get this H is also yes. And the Q and the W. Yeah. Because if we don't know this the equation, it may be quite hard for us to calculate how the Q transfer to W. Yeah? So this is our aim. Why we need to why we need to calculate this, to calculate the internal energy by this equation. This is our aim. Okay. Now, I think you can think about if we want to calculate du, in which equation we have known included du. Do you remember? In which equation? Maybe this one. Do you remember this one? Yeah, this is the we can say the energy equation for closed system. Yeah. Okay, now we can say okay, du. Then du is equal to dq delta q plus pdv. And then delta q, do you remember just now we talked about it?
It's right
Is C dt. Yeah? We just talked about this. So we talked about it quickly, but I think you know it. Yes? You know it now. And then plus pdv. Okay?
That's all right.
This one is not so, maybe we can say it is a little complicated. We want to make it simple. Okay? Okay. So now we say we add a condition for a constant volume. Constant volume. Okay? So now we know for constant volume, dV is equal to 0. Yeah?
Yeah.
Because the volume will not change.
Yes.
So dV is equal to, so now we get du is equal to, but here, remember, here is C, but here is CV. Yeah? CV dt. This is the reason why we say du is equal to here. This is the reason why we calculate this equation. Here, we get maybe one question. I think you can think about it. We add a condition over here. This equation should only be used in a constant volume. Yes. But if a large process is a constant pressure, do you think we still can use this equation?
Where?
Can we use it or not?
When?
Only for constant.
for last, when we get this equation, we under maybe you can say concentrate here, a constant volume. Yeah. So for last process, it's a constant duration or constant thermal. Do you think we can use this equation?
No.
Yes.
No.
No. Yes. Why? Why yes? Why no?
No.
Thank you. I think honestly, sometimes I just say, if my English is good, if my English is good enough, I think our class will be interested in because I love you guys. You can discuss your class, I think. So why we can use it or why we cannot use it? I tell you, just remember one thing. The U is a state parameter. Do you remember we say a state parameter is only related to the initial and final position, but it is not related to the process. Yeah?
Wow.
Do you remember this one?
Yeah.
Yeah. For example, if here, maybe we need to calculate the U. This is a constant volume processor. We need to calculate the U2 minus U1. Okay? This is a constant volume processor. And then we can say, okay, this equation can be employed here. Yeah? Do you remember this? I think you agree with it. Yes. But if we change this to a constant operation process, and if we try to calculate the U2 minus U1 through this process, I think we cannot use this equation yet. But we can find another process like this one. Yes?
Yeah.
And then we can use this equation to calculate the U2 minus U1. Yeah?
Yeah.
And significantly, this U2 minus this U1 is equal to this U2 minus this U1. Yeah?
Yeah.
So remember it. So when we get this equation, we add this constraint here, a constant volume. But the equation can be used in any condition. Okay?
Yeah.
Just remember it. And here is another equation used to calculate the assumption. I think you know how to get this equation. Because firstly we need to think in which equation we have learned include assumption.
Steady state equation.
We know this one. Remember, there are Q minus or no is equal to dH minus V dP.
Yeah.
Yeah. Okay. We can add a constant pressure, and then we get dQ is equal to dH, and we know dH is Cp dt. Yes.
Yeah.
Yeah. So remember it. Okay.
Yeah.
Now we know how to calculate the internal energy, and we also know how to calculate the assumption. I think we want to know the relationship between Cp and Cv now. We just tell you that Cp is greater than Cv, yes?
Yeah.
So why? Can we prove it? Of course we can. And here, here is not, the blackboard is not big enough. Okay, I need to. Okay, now, do you remember this equation the definition of assumption. Do you still know the definition of assumption? H is equal to U plus PVM. And then we know, yes?
Yeah.
Now we can change it. We have found you found the relationship between CP and CV. This is CP, this is CV. So CP is equal to CV plus R. So this is the reason why we can say CP is greater than CV. So now we also this argument this is not important. Okay. If we get this true, I think we will try to calculate the CP and the CV because we know this is a constant for a specific gas. Yes. This is a constant. So we say, okay, CP maybe CP and CV can all be use this R to calculate. But we know this is a little hard for us to calculate. So we need a large ratio of specific heat. This is the definition. K is the ratio of specific heat. And now you can calculate the CP and the CV. Do you understand this one?
Yeah.
Now, if we give you a specific gas, for example, oxygen, do I read it to write about this one? Okay. And then we can find out it's K and it's R, yes? And then we can calculate the CP and the CV now. So this is the reason why we need to define a ratio of specific heat. Okay, now let's go to the last part. The entropy of ideal gas. And the entropy. Yes. So, okay. We have 6 state planet, and PVT is basic planet. U, we can use this equation here, yeah? And H, we can use this equation to calculate, but we don't know how to calculate the S. Yes. So here, we'll show you how to calculate the S. So here are 2 equations. How can we get these 2 equations? Okay. I think you don't need to remember this one now. You need to remember what I write here. Okay. I'll show you how can we get these 2 equations. First, if we want to calculate the ds, we first need to think in which equation we had alone include the ds. Do you remember in which equation? In each equation, we learn the ds. Where? Do you remember this? For what's molecular size? Maybe you forgot it. Maybe in class, in lesson 1 or lesson 2. When we define, we say because the W is P dV, yes? So we say this is a force, and then here is a distance. Yeah. So we know the T is the force also, so we need to find the I know this maybe is not a distance. It's maybe I need to get hammer from one first. Okay. Do you know what it is? It is a displacement.
Displacement.
Yes, displacement. Yeah. So this is a displacement. We know for here. This is force, and then this is displacement. Yeah. For this one, this is a force, and this is a displacement. Yeah. So we know this is a force. We don't know which one is the displacement. So we pick the H. We say, okay, this is a displacement. Do you remember this one?
Yeah.
Okay. Now, if you remember this equation now, we can say, okay, ds is equal to delta q divided t. And the delta q, so how to calculate delta q? Delta q is equal to, we have two equations to calculate delta q. It's equal to du plus p dv.
Yeah.
Yeah?
Yeah.
And now we know du is equal to cv dt. And yeah? So now we can get and finally, so we say, okay, S2 minus S1 is equal to so this is the equation. Maybe is this one? Yeah? Yeah. So now do you know how to calculate this one? How to obtain this equation?
Yeah.
I think it's the same. If we here we not use this one. If we like this, yeah, and then we know Cp dh is Cp dt, and then if we times the p, then divide the p, pv minus PV is R, and dP divided P. And then we get this. Yeah? So this is maybe this equation is the same as this one. So now, okay, you cannot see it. Maybe you can
how you
this is du is equal to
Yeah.
CVD.
and then this word we how
We here we times PV and then divide V, okay? And then here like this one, and then we change the PV, dV, this one. And then PV is equal to RT. Okay. Do you get it? Okay. Now, I think these two equations is maybe we can say it's quite good. Yeah. But we have a problem. For example, if a process is a constant volume or a constant pressure, a constant pressure process. So, which equation will you selected to calculate the change of some entropy?
Second one.
Pressure.
The second one.
Mm.
Are you sure? The second one?
Mm. No, constant pressure. The first
Pressure.
one.
For constant pressure is the second one, and for constant volume is the first one. And if we say a constant thermal, so which one?
Constant.
Constant thermal
Temperature. Constant temperature.
temperature, okay?
Constant temperature.
Which one?
None of them.
Do you remember I just discussed with you the entropy is a state parameter. Yes?
Yeah.
And then if we calculate, no matter it is a constant volume or a constant CP, another constant pressure, the result
That's one.
is 2 minus S1. Must be the same. Yes? Do you agree with that? But now we get two equations. Yeah?
Mm.
So which one is right? I'd like to tell you. They are the same.
Mm.
You can try. Okay?
Mm.
Do you know CP is equal to CV?
Plus R. Plus R.
Sorry, I forgot. R, yeah, R. Yeah. And we can put here, to here, okay?
Yes.
Put this one. And then, now we can say it's equal to CV. And plus R. Like this one.
Mm.
Yes?
Yes.
We also need to know PV. We know PV is equal to RT. And this means T2 plus T1 is equal to P1V1 plus P2 V2 P1 V1.
Mm.
And now we put this here. Just this part is equal to P2 V2 plus P1 V1, and that is equal to yeah. And now we have found this part is equal to this part, yes? So now we get, maybe I can add here. We have found this equation changed to this one, C1. And here is R here. Yeah?
Mm.
And this, do you think it is the same as this equation?
Yes.
Yeah, it's the same. Yes?
Yeah.
Yeah. So, again, maybe you can say we prove for state parameters, no matter in which process is the result, the change of the parameter is the same. So, in the next, in the future, if you need to calculate the change of entropy, this one is right. This one is right also. Maybe you can take a photo. Okay. For the process of how we obtain these two equations, I think you don't have to know it, but you should remember these two equations. You should know how to use these two equations. Okay. Okay, here is exercises. I think you can try. Maybe we don't have a lot of time on this, but you can try. Okay. What? Yeah, okay, you need to take a photo. Okay. Oh, I don't think you need to take a photo because you can get a PowerPoint. You don't need to take a photo here, but I think you can take a photo here. Maybe if you wanted to know how we get these two equations, I think you can do it. But this you don't need to try. Oh, I know why you need to take a photo because you need to count. Oh, I understand it. Okay. Here, I think you can try because sometimes it is a little hard for you to understand what I said, but if we finish the exercises, that will help us a lot. Okay? Try. You will say the tolerance of here. Literally, yeah. Do not change it. Initial pressure is this one. The initial temperature is this one. And the final volume is 3 times the initial volume. Do you understand these things? The final volume is 3 times the initial volume. Because I'm not sure I translate it to what. Okay.
Oh, yes.
Initial volume is 3 times.
The final volume maybe is V2.
Yeah, it's
V2 is 3 is equal to 3
V1.
Okay. Because I'm not sure because I translated right note. Let's suppose that the nitrogen has ideal gas properties. Trying to find one. The final temperature of the gas, the final pressure of the gas, and the change of entropy caused by the change of state of the gas. Maybe we can get the answer here, because we don't have enough time to read this one. Okay. And when you go back home, I hope you can try to finish it by yourself. Okay. Here. This is our answer. Because the internal energy did not change, so consider U is only the function of T, and hence T2 is equal to T1. Okay. And then considering PV is equal to RT is equal to a constant. Yeah. And hence here. I think this is not hard for you. Then we can calculate the T2. And for 3, we need to employ these equations.